Some light has been switched off. Restart or? Okay, so let's resume. So this is what I was just telling you, that these strategies now in a dynamic game are functions for each player, which map his that player's information sets to the actions that are available. This is where we ended. Okay, and now as we can talk of an Nash equilibrium in this space, but we can also allow for because there is this, we can also allow for this instrument of commitment, and that commitment leads to a different concept which is called the Stackelberg equilibrium. So in this case, your player one was committing to a strategy first, announces it. Player two responds to it, as knowing that strategy, and so his best response is going to be a function of what was announced, and player one then takes into account this response, this functional dependence. I think this is gone now. This battery is gone. Okay. Yeah, there's no light, there's no laser here. It's okay, but it's so the player Stackelberg leader anticipates this best response as part while announcing. Now, this is now basically bringing us to the threshold of this whole topic of information in games, and that's from where I'm going to take off into into strategic communication. Yeah. Yes. Yes. Sorry. So in the Stackelberg equilibrium, or rather the concept of the leader, is it the person who's playing first? No. 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 The order of commitment is to be defined separately. Okay, separately from the, so you'll get one solution if one fellow commits, another solution if another guy commits first, and so on. Yeah. So order of commitment is distinct from the order of play. Yeah. Okay, so now let's talk about information in games. So there are two sources of loss of information in a game. Okay. So is that thing ready? Or not? The pointer? No, okay, it's okay, no problem. So there are two sources of loss of information in a game. So a player may have lack of information due to two reasons. One first is the any loss of information that is happening, lack of information that is there before gameplay, and the other is what is happening during gameplay. So if you look at this diagram that we had here, right? So in this sort of figure, the loss of information, the player two has partial information only, that is sort of intra-game information which is lost. So during gameplay, he doesn't know what player this player has picked, but he does know what the tree is. He's also aware that he will not have this piece of information while playing. Okay, all of that he's aware of. So he's aware that there is such a tree. He's aware that there is going to be some amount of ignorance here. But so this loss of information is this, what is the, which is that this is during gameplay, and so this lack of information. So this is what we call imperfect information. Okay, so during gameplay, a player may or may not have the exact knowledge of the state of the game, which tree he is on, which node of the tree is on. So this lack of information is due to not knowing the actions played by the other players. It could be forgetting his own actions. It could be forgetting what he previously knew, and so on. So this is like one. This leads to sort of very esoteric type of phenomena where player is sort of absent-minded. Forgets what he previously knew, and this leads to some very interesting issues. And you may say they're not of practical importance, but many game theorists are absent-minded. So it's a very valid issue. So then there could be reasons like noise, limited observability, limited memory is important, and so on. But the main point is that while strategizing, players are aware that they will not have access to the said information. Okay, this is part of the knowledge of the game, part of the knowledge information structure that is assumed. Okay, so player and in other words, they have the knowledge of the entire game. The other type of loss of information could be incomplete information. Incomplete information is essentially one where the player does not know which game he is in. Okay, so he does not. It's not that he does. It's he of course, in addition to that, he may not know which node of the tree he is in, but he doesn't even know which game is being played. Okay? So the way you model this is that a game is chosen at random by nature, according to some distribution. Players do not know which game has been chosen. Okay? So, for example, if you are a security officer at an airport, you see a car approaching you at a very high speed. You do not know if that car has a regular passenger or a drug trafficker or a terrorist. You have to take an action not which is appropriate for the situation without knowing which of these is the actual game you are in. Right? There are multiple, so essentially in that sense, you have multiple possible game trees, but a player does not know which is the realized tree. Okay. And in addition to that, individual trees may have imperfect information. Like, for example, you may not clearly see who's sitting on the front seat of the car and so on. That kind of stuff could also be. Okay. Now, a particular case of this kind of incomplete information is what is called a Bayesian game. A Bayesian game is the following. So, in this case, what nature does is it, uh, it so each player, we say, has a set of types. A player can be of multiple types. So, for example, the fellow who is coming to the airport, it could be of type terrorist, drug trafficker, normal. Any of these could be the player. Nature chooses a type at random for you. Okay, and a player is aware of his own type. Okay, so nature chooses this profile of types at random for all the players according to some known distribution. Each player is made aware of his own type. So the terrorist knows that he is a terrorist, the normal passenger knows that he is a passenger, but the security guard does not know what that fellow is. All right. So, and then therefore the payoff then depends on the actions that are chosen and the vector of types of all players. Now, because a player knows his own type, but not the type of the others, the strategy that a player should now choose is a function from his type, set of types, to the set of actions that he has available in that type. Okay. So, for example, if the set of actions will be different for a terrorist or this or that, and the action therefore is a function of his type. Okay, and if you're allowing for mixed strategies, then the set of strategies is a function from his type to the probability distribution on the set of actions available in that type. Is it clear? Okay. So and because each player knows his own type, what each player is actually maximizing is not the expectation, but actually the conditional expectation of his payoff given his own type. Okay? So each player I maximizes this J bar of this given Ti, where Ti is that player's type. Now I forgot, but we are in a communication conference, so type here does not mean the same thing as types in information theory. Okay, that like I've used the word. Let me use for that empirical distribution for that. This type is not this. This is what I mean by type. Okay. Later we will also see that the two types will coincide, but let's not worry about that right now. Okay, but okay, so yeah, so this is therefore, so you see here, I'm taking a conditional expectation over the t minus I given ti. There is also there is also an expectation with respect to all the mixed strategies, any mixing that the players would be doing, which is the randomization they choose, with randomization with which they choose their actions. So there are two sources, therefore, of randomness: one which is chosen by nature, and the other which is chosen by the player. Okay, so the expectation is then taken over all this. So and it's conditioned on player eyes test. Okay. Now, why this conditioning? So this is basically the maxim or the axiom that we have, that whenever a player has some information, and the thing that a player should be doing is maximizing his expected payoff given that information. Okay, that is the notion of rationality. Essentially, it comes down to some rationality axioms, that the right thing to do when you have information is to maximize the conditional expectation of your utility given that information. Okay, so that's what Bayesian rational means. And then with this setting, you can define what is called a Bayesian-Nash equilibrium. The Bayesian-Nash equilibrium is one where essentially a Nash equilibrium, but given this. Okay, so it's a little bit of a mouthful to read this out. But essentially, no player would want to unilaterally deviate from his strategy, unilaterally to deviate, assuming his type, and for this has to be true for every type of every player. Okay, so and initially this seems like a very demanding concept, because this is to be true for all TI, right? But actually, it's not that complicated. It turns out that essentially every type of every player becomes a distinct player in some way. So you can basically take this sort of a game of incomplete information and write it as a game of imperfect information, where the players are the number of types times the number of players. Okay, that sort of thing can be done, and then this actually gives you that there is always a mixed strategy, a Bayesian Nash equilibrium. Yeah.
And this different trees could be the branches of that.
Yeah.
Will it become an imperfect?
Yes. That's exactly how it is done. So this reduction is done by introducing this player nature. I have actually skipped through that. So you introduce a player zero, which is nature or God or whatever, and that fellow picks the types of these players. Players, their information sets are such that they see only their own type. Okay, that's how you create the information sets, and then you can write an imperfect. Okay, now a particular setting where you have incomplete information is what are called sender-receiver games. And now we are basically getting more and more into the issue of information. So the sender-receiver game is the following. A sender-receiver game is a two-player Bayesian game with two players. One is a sender of information, the other is a receiver of information. Sender of information can only send information. He is the one who has private information. So he has a type which is chosen. Okay. The receiver doesn't have a type, but does not know the type of the sender. The receiver has essentially a trivial type, only one type. So nature is picking the sender's type, revealing that type to the sender, but not to the receiver. Okay. So communication language, there is a source. Sender sees the source. It has to be sent to a receiver. Receiver does not know what the source is. Okay. The sender has private information. Now here's an important thing. The sender has private information, but he does not have a choice of actions. Okay, in the sender receiver game, sender has private information, but no choice of actions. That means the sender, so recall what I said about actions, and I'll explain this again. See, action is one that directly appears in the cost function. This is what we call action. Okay, so action is the one which directly appears in the cost function. Now, if the sender has no action, doesn't mean that he has nothing to do. He can send a signal. Signal is something that is some decision, but it doesn't affect the cost function. The cost function is independent of that variable. So what is the use of this signal? Well, this signal goes to the receiver and it changes the information of the receiver. Okay. So the sender has private information but no choice of actions. The receiver, on the other hand, has a choice of actions but no private information. Okay. So the sender is going to send this piece of information to the receiver. Okay. The receiver then sees that some piece of information, the thing that was sent by the sender, and then based on that takes an action. And that action determines the payoff of both sender and receiver. Okay? So the sender has a type. Based on the type, he sends a signal. Okay? And based on the signal, the receiver takes an action. That action determines the payoff of both. This is the setting. Okay, so here formally, yeah.
What's the issue with thinking of the signal of the sender itself as an action?
It changes qualitatively the game. It changes the game significantly. It leads to, so in control that it leads to what is called a dual effect. In other cases, it's what leads to the distinction between cheap talk and expensive talk. The very fact that I am uh, that signaling costs me something, okay, means that I have means that you have something to infer from the fact that I have signaled. Okay, that is that it has a like a qualitative effect on. I can maybe if I have time I can talk about that. Yeah.
Then when we say that it affects the payoff of both sender and receiver, is it implicitly assumed that there is some kind of feedback channel?
No, no, I'll tell you. Let's just look at the formal model. So essentially, the game is then specified by just these things: type of the sender T1, types set of types of the sender, set of actions of the receiver S2. Okay, the probability distribution P, which is the prior with which the types are chosen, hmm, and J1 and J2, which are the payoffs of both players. So what is missing here? T2 is missing, which is the type of the receiver is missing. There's no T2, the trivial type for the receiver. There is no S1, which is the action of the sender. Okay. Now, what the sender has though is this fourth last thing that I mentioned is a signal space. The sender can send a signal, which is let's say stochastic signal. So he's going to send a randomized thing. I think this is again called. Okay, he sends a random thing. Is there a stick or something here? No, no. Okay, it's okay. So he sends. So the sender strategy is a conditional distribution. Given his type, he chooses a distribution on the signal space. It's a it's a it's a function that maps types to the set of probability distributions on the signal space. Okay. Receiver's type, receiver strategy is a function that maps the signal that he receives to a probability distribution on actions. Is this clear? And the receiver wants to solve this. The receiver wants to find a gamma 2 to minimize his cost. Now, the cost of the receiver depends on the type of the sender and the action that he chose. Okay, and you can factor out the joint distribution in this way. So it's effectively the action is chosen with probability gamma 2 of S2 given sigma, where sigma is the signal, and the signal is chosen with probability gamma 1 of sigma given T1, where T1 is the type or T1 is the source or whatever. Okay, and that gives you your expectation. Yeah. Yeah. Both know P. So we are in a decision setting, not learning setting. So P is known. Hmm? Yeah. Okay. And then sender similarly wants to choose a gamma 1 to minimize his this thing. See, remember now J1 is a function of S2. So the action that the receiver chooses is the one that affects sender's payoff also. And of course his own type. Okay, but remember here, so here actually, because he knows his own type, right? Effectively, what I've done is taken a conditional expectation here. I've conditioned on T1. So this is, there's no summation here over T1. Is this clear? Okay, so this is what is called a sender receiver game. Now, if you read between the lines, you will see that there is basically a communication setting here, right? There is a sender of information, there's a receiver of information. The sender is what does the sender send? The sender sends, you can in a communication setting, he sends basically a code word. The receiver, but the final payoff of both depends on what the receiver outputs, right? Which is the action of the receiver. Okay. Now, if the power required to send or something like that, that also affects the cost, then there is a case where the sender's action also is then the signal is an action. But here, in general, we have a setting where there is no such thing. Where there is no. Generally, we have a setting where there is no such cost. The cost depends only on what the decoder outputted at the end, and the sender's type or the source or whatever the source was. Okay. Okay. So this is your sender receiver game. Now here, as I said, now let's bring in commitment into this. Okay, you can do commitment in two different ways, two different types of commit. So again, as I said, I want to get this across. Actions versus signals. Action is that which directly appears in the cost function. Signal is any other decision that doesn't directly affect the cost function. So signal basically goes into the conditioning. Okay, that's there with the recipient of the signal. Okay. Now, yeah. So there are two settings that we can consider as far as when it comes to what kind of commitment is being made. The first setting is where the sender commits first. This is what is called the signaling setting. Okay, this is called a signaling game. So which is that the sender is the leader, Stackelberg leader. The send so in the signaling setting, the sender of the information is the leader. And so if the sender of the information is the leader, what is the goal of signaling? The goal of signaling is for the sender to influence the receiver. He wants to send a signal to influence the receiver into taking a certain action that will be beneficial to him. So what his goal then is to shape the information that the receiver has. Now, remember what I said, when you get information, what are you supposed to do? Just apply Bayes rule and update your prior, right? So what the receiver basically does when he gets information is that he computes a posterior distribution of the type which he did not know. He computes a posterior distribution of T1. Earlier, so before receiving the signal, he just knew that T1 was chosen by nature according to probability, some prior distribution P. Now he's got this signal, so he has to now update his distribution to this one. So it's the new distribution P of T1 given sigma, the signal that is actually received. When the sender is the leader, the goal of the sender is to get the receiver to shape to reduce a favorable posterior distribution about the source. Okay, this is this is why this setting is what is called persuasion. It is to convince him through say, by sending him information, you know push notifications on your mobile phone or whatever. All of these things are some form of persuasion. Okay, last date for this, last 15 minutes left for this offer or whatever. All of these things is a form of persuasion. Okay, so the goal of the sender is to shape the posterior distribution of the receiver. Or it's called, as I said, persuasion, also called nudging. Nudging in the language of Taylor, who got the Nobel Prize I think 2017 or something. Okay. This in this case, we actually there's a hint of information theory here also. Actually, you can talk of two types of equilibrium. Now, with this kind of I have defined an order of commitment, so I can talk of a Stackelberg equilibrium now in this space, and it turns out I can talk of two types of equilibrium. One is what is called a pooling equilibrium. The pooling equilibrium is one in which senders of all types choose the same strategy or choose the same signal or same strategy, same signal. That means regardless of the type of the sender, the signal that the receiver gets is the same. So the receiver has no way of from that signal to tell whether the sender is of this type or that type. Okay, so if in that sort of in other words, the information content in that signal as far as reducing the type is concerned is zero. There's no information content in it. But another extreme is what is called a separating equilibrium, in which distinct senders end up sending distinct signals. This distinct types result in distinct signals. Okay. So the other extreme is what would be if I say, well, the receiver is committing first instead of the sender committing first. Now, if the receiver is committing first, then what is happening? The receiver does not know the type, okay, and he is just committing a certain strategy even before the sender has. He's announcing a strategy, and the sender has to then respond to that. So then in this case, this problem is one where the receiver announces a policy for choosing actions as a function of what signal the sender is going to send, and the sender has to now think, okay, what am I going to send? So this results, and the receiver anticipates the response of such policy. So this is a different setting. This is a setting in which there is the receiver is basically coming up. You can say there is a there is what we call a principal and an agent. The principal is one player, the agent is another player. The principal basically wants to get some task done in some field, okay, at which there is some information which he does not have access to. So he delegates that task to the agent. The agent actually has the information in the field. He has his type, which is the so sender has the type. He goes there in the fields. He has the information. Okay, and he performs the task. But the receiver has to come up with you could say come up with a with a contract with, that rewards the receiver has to come up with a contract if that is a function of only what the sender actually signals to him, because the receiver has no way of measuring what is receiver cannot measure what's in the field. Only the sender can measure that. So the receiver has to come up with a contract with as a function of what the sender is telling him. So therefore, the receiver has no way of knowing how hard the agent, how hard his agent is working. He has delegated this task to do this, go read this paper, but you don't know if this fellow is actually reading the paper. Okay, so 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 this leads to the situation is what is called moral hazard. Okay, it's again a known situation in games. Another related phenomenon is what is called adverse selection. That's not as relevant here, but moral hazard is a known situation in which, so basically the once the contract is made, it basically it doesn't remain, because the sender has the information. It doesn't remain optimal. There is a it's possible for the sender to basically just use the noise to show that to substitute for his hard work essentially. Okay, so there is no scope of remember because the so the see here the this posterior this update, right, updating the prior to the posterior. This for me, what do I need for this to do this? I need the prior and I need the conditional distribution of the signal given prior. Now, how will the receiver know that conditional distribution? He will know it only if the sender has announced it first. If it is not pre-committed, there is no way for the receiver to do apply Bayes rule. So therefore, in this setting where the receiver is announcing first, there is no scope for the receiver to do any Bayesian update. The receiver basically works with just the prior distribution. Okay, is this clear? Okay. Okay. Any questions? Anything on any online questions? Nothing. Okay. Questions from the audience? Okay. So fine. Okay. So let's see what sort of granularity we need to go in. Okay, so this is basically now introducing you. I've introduced you essentially to essentially given you enough hints that there is an angle of communication present in all these strategic interactions. So now we can actually get formal and do an information theoretic analysis of such situations. Okay, I have 3 case studies planned, and uh, some of them are my own results. So those I have a little more. I probably over budgeted my slides for that, so I'll probably run over those. Let's see. Okay. Okay. So here's this here. So we'll look at the first setting, which is the receiver commitment first. Okay. Receiver commitment is one. So receiver commitment is is sort of trying to distinguish between different types of senders, or what is called a screening setting. Essentially, why am I using the word screening setting is because we do not know how hard the sender is working. Essentially, we would like to distinguish between different types of senders. Okay? Yeah. So here's the setting related to this. So this is a COVID application. you remember the early days of COVID, people were coming from all over the world and they had to be segregated in, to, okay, for further testing, to quarantine or send them home and so on. So the health officer and essentially, so there was obviously there is some scope for the sender to misreport information here. And the goal of the health officer is to come up with a he wants to do the segregation based on a questionnaire, right? So if you go to when you're returning from abroad to India, they will ask you, are you carrying this, are you carrying that, etc. There's some standard questionnaire which is printed out, and this questionnaire is printed out before I know what kind of traveler you are, right? So I am announcing this questionnaire first, okay, so as a receiver, I'm pre-announcing this questionnaire. You have to respond to that question. So the problem for me as a receiver, for the questionnaire designer, is how should I make this question, right? So this is basically the problem. So you have travelers arriving from various parts of the world. They have a tendency to misreport, which means they have a utility function which doesn't necessarily align with truth telling. Okay, and the health inspector's challenge is to come up with a common questionnaire for all travelers and ascertain as many true travel histories as possible. This is the problem we want to solve, and we want to ask, okay, how should such questionnaires be designed? Okay, so here's the setting. You have a sender who's your traveler who sends a response to the officer. The response is the response to his questionnaire, and the officer wants to create the sender has a true history, travel history. The officer wants to estimate that true history. Okay. Then the agent is non-cooperative. That means the sender is non-cooperative and may not report its information truthfully. You can apply this thing, play this game on whatever cyber physical systems, this, that, whatever. We'll skip over that. Okay, so this is the problem of extracting information from the sender. So the question is, what is the strategy? Should be the strategy, and what should be the questionnaire? How should the questionnaire be designed? And what is the maximum amount of information that you can get from a sender like this? And I have to define what it means, what amount even means. Okay. And similarly, so naturally, once you start doing information theoretical analysis, you take limits and all that. So are there fundamental limits to this whole exercise? Okay, this is the question. Okay, I will also look at a setting in which there is a channel in between. So once there is a channel in between, the game is not just of incomplete but also of imperfect information, because there is intra-game information that is also being lost in the process. Okay. So first, let's take a setting of noise. Take a noiseless setting. So here X here is your sender's type or your traveler's type. It is a vector from some space whose coordinates are from a space X. X is some alphabet from 0 to q minus 1. Okay. Now, how do I interpret this in the traveler segregation problem? X is then the set of possible locations. N is the length of the travel history. Q is the set of possible locations. Okay. It's the number of possible locations, and N is the length of the travel history. Y X is the actual travel history that the traveler has. Y is the travel history that the traveler says he has. It is what he reports to the health officer. So, for example, at that time, I think Iran and Italy and so on initially had most of the COVID cases. You ask him, which of these is your travel history? You were in France, then you were in Italy, then you were in Iran, then you were in whatever. He will say, no, 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 I was not in Iran and Italy. Yeah, that is the reported travel history. Okay. Now, of course, there can be more complicated things. Like there may be, there could be something like there could be hotel stamps or passport stamps and whatnot by which you can constrain this. You can say, well, the certain types of histories are not possible. He could not have possibly been here. He was definitely on this location at this time. So some part of this vector X can be constrained and so on. So let's take for simplicity that there is no such no such constraint, and this guy is just just saying that there is some this thing, and he has some true history, and he has some reported history. Okay. this seems completely very, very loosely formulated, because it seems like then what, anybody will just get away with anything, right? But you will see that there is some structure here. X hat is what now the health officer is not a fool. He's going to look at what you said and then map that to a deduced history. Okay, so he takes the history that you reported, which is what is there in the questionnaire, and from there comes up with the deduced history. Okay, so the sender strategy then is to is this function Sn. So now, because we are in this information theory thing, I'm going to keep, there's going to be this trailing n everywhere. Okay, remember that is your block length, which will then run to infinity. Okay, so here the simple setting is there's no noise in the channel, so that means that this fellow marks the questionnaire is seen noiselessly. The noisy channel would be that we mark the questionnaire, spill some coffee on it, the coffee spilled questionnaire is seen by the receiver. Okay, so that's a noisy version. Same. Now, the receiver strategy, as I said, is to look at what the response is to the questionnaire and map it to an estimate, history estimate. But in addition to this, now because I said this will look very loosely formulated. In addition to this, I'm going to give the receiver one additional instrument, which is that I'm going to give him this thing delta here. What is this delta? Delta is what you can interpret this as as saying that if he sees, so if some response comes here, which is going to be mapped to delta, it means that that response was actually not present in the questionnaire. Okay, it's not part of the questionnaire at all. So in the questionnaire design, you have that option is actually not present. So this delta then is essentially some action of the receiver, which gives minus infinity as payoff for the sender. Because it's something that the sender just does not want. So it's like a punishment for the sender or whatever. Essentially, it is an option that is not present. Okay, because it's just not possible to map it to that, because a rational sender will obviously map to one of the other responses. It's something that the receiver is not going to map to that. So this is just a device to eliminate some options from eliminate some options out of x raised to n. So any sender will always, so a sender will always map uh, will always send a y which the receiver is not going to map to delta. Okay, he's never going to choose a y which will be mapped to delta. Okay, so what are the objectives? Let d of g and sn be, this is your decoding set. Okay, so this is what the sender is, what the receiver decodes correctly, is the number of histories that the receiver is able to perfectly recover. Okay. The aim of the receiver is to maximize the size of this set. So he wants to design a GN that maximizes the size of this set. The sender has a utility. Sender has a utility which depends on two things: his own type, which means his own history, and what the receiver or health officer reduces his history to be. So it's a function of x and x hat. So x is his own history. X hat is what the receiver will conclude his history to be. Okay, and so this is the n block utility I have, and that is given by this average of the single letterized utility. So u here is their single letterized utility. Yeah. No. So d of gn sn is equal to the x such that gn of sn of x is equal to x. It's those x's that are correctly recovered. Yeah. Okay. So this is your single letter utility. And as I said, I'm going to assume that if delta comes up here, if the receiver recovers delta, right, then you get minus infinity as the payoff. So delta is something that is never preferred by the sender. So in other words, if y in xn is such that gn of y maps to delta, gn of y is equal to delta, then y is effectively not even a feasible option for the sender. It's as good as not being there in the options that he can report. Okay, so actually what I've done is, so here, right, effectively what I'm saying is this is although I've written here xn as the space in which y can lie, it's not all of xn. Okay, some sequences from xn have been removed. Yes.
So that you require that y take values in respect extent. Isn't that unreasonable? For
Sorry.
instance, why you require to take values in respect extent?
No, that's not unreasonable.
For instance, I mean, XN could be the list of countries,
Mm.
whatever has been said, and questionnaire could be like daily temperature over now.
So X is, yeah. So X is the set of countries.
Yeah.
Okay. N is the length of the history.
Right.
So essentially, the universe of responses is all possible strings in Xn. That's what I'm. So the questionnaire effectively, without loss of yeah. So I skipped over this, but without loss of generality, a questionnaire can take the following form. So basically, I think that's the. I'll just come to that. Just give me 1 minute. Let me just quickly tell the solution concept. Okay, so we are posing this as a reader follower game with the receiver as the reader. So this is a screening setting. Receiver commits first because the questionnaire is printed out before the travelers arrive. Okay, and the travelers are aware that this is what is going to ask me. Okay, if and so if the receiver plays gn and the sender observes x, then the sender basically will respond with his best response. Okay, which is he's going to choose an sn which maximizes his n block utility. Okay, here. Now this n block utility, recall, is the average of the single letter utility. So he may gain some from misreporting, he may gain some from speaking the truth, etc. Many so an average of all of that is what he's getting. Okay. Yeah. So that is the setting, questionnaire setting that I'm assuming. Yeah, yeah. So you will that there is I have an answer to that. So that's a slightly different this thing. You are right. I mean, so then we have to look at a different concept in which no one is committing, and then you are simultaneously playing, and then in that case you are looking for an Nash equilibrium. In which case the analysis will take a different route. It will lead to a different the information which recovered, etc., will be different. Results will be different. So this is I'm assuming this setting. Uh, Now you can try to work around that by saying about this objection that you have is valid. He doesn't know what he's going to think about the response, right? So now that you can work around that by saying that by putting in basically in the questionnaire you put in an additional line basically saying whatever you take will be automatically applied. Okay, that's part of the that's part of the questionnaire definition itself. I mean, so we have to even if you try to really make this problem formal, we really have to also define what is a questionnaire in some sense, right? In a concrete sense. So here in this case, for example, I have a multiple choice questionnaire in which only tick the best that applies is the mode of answering. You cannot tick multiple. You cannot more than one option is not allowed and so on. So all of this I have to define this whole universe of what a questionnaire actually is. So in that I need to plug in this particular assumption that whatever will you tick is the one that will be selected. Yeah. So the receiver plays GN, announces that, sender observes, responds. Receiver anticipates this response and then looks at the whatever is the worst case that the sender could have responded with, and then tries to decode as many as possible through that. Okay, and this is your Stackelberg equilibrium. Good. Okay, so here is for so Chandramani's question. Right? So so here is a sample questionnaire, right? So suppose here's a naive questionnaire. There are q possible locations, q raised to n possible histories. What I do is I create a questionnaire which says which of the following is your true history. X1, xn, x1 dash, x1 dash, x2 dash, xn dash, etc., etc. There are q raised to n some possible history. So all possible histories are there. Now, suppose there is a say for COVID-free island somewhere, okay, some location N, in which there was no COVID. If I included all possible histories in my questionnaire, because the setting is so loose, right? Essentially, the receiver can just report that. So everybody We'll just tick LLL. We were all at this island. So all of them will say that they were on that island forever, on all the end days. Right? So therefore, what will the health inspector therefore be able to recover? He will be able to recover only the sequence LLL. Only the guys who are truly on that island will be recovered correctly. Everyone else would have misreported. Right? So what does this mean? This means that because of this way this whole setting is, if the receiver wants to extract any meaningful amount of information, he has to eliminate some options. He cannot possibly include everything. If you include everything, it creates too much space for everyone to lie. Okay, so therefore that is the reason for that delta option. Essentially, that when you map some things to delta, essentially those get they get excluded from those from feasible responses to the question. So the form of the questionnaire that the sender then sees is that although q raised to n are the set of possible, there are that many possible histories, only a subset of them are actually listed. Okay, and then the questionnaire says you pick the one that best represents your situation, or the one that best applies. Okay, that is the question. Okay, so now so the dilemma for the receiver is basically this: that if there are too many histories included, it creates space for people to lie. If you include too few, then you are not recovering enough information. So somewhere in between is the optimal number of histories to include, and that's your optimal questionnaire design question. Okay. All right. So you can see there's a combinatorial angle here. So let's define this. This is called a sender graph. A sender graph is one where there is an edge between two sequences x and y. If the sender has no incentive, uh, uh, has an incentive to report one as the other. Okay? Not no, it has an incentive to report one as the other. So there's an edge between x and y. If if either unxx is less than equal to unyx, or unyy is less than equal to unxy. So he has an incentive to report either x as y or y as x. So when his true history is x, he would want to say it's y, or when his true history is y, he would want to say it is x. Okay. All right. So here's the theorem. So for all equilibrium strategies, Stackelberg equilibrium strategies, the receiver recovers the largest independent set of this graph. This is so what can the receiver recover? He recovers the largest independent set of this graph. And here is your achievable strategy. What you do is the following. This also answers partially Vaibhav's question. What does the receiver do? He basically prints a questionnaire in which only the independent set of this graph are the set of options. So that this graph has x raised to n, q raised to n many vertices. He picks the independent set from there, publishes only those in the questionnaire. The receiver now says, and moreover, he also announces that I'm going to take this as face value. Whatever you report, I'm going to take it as face value. So my decoding is going to be this. So if this thing is in that option, I'm going to just apply an identity function. Everything else is being mapped to delta, so it's as good as not there. So this is the operational interpretation. So now the operational thing, there are no codes here. Okay, there are no codes. There are equilibria in place of codes. The equilibrium strategy of the sender is of the receiver is to play this. It is to do this, and this operationally now has the meaning of the optimal question. That means it's a questionnaire in which the certain options are present, and the receiver then takes whatever you take at face value. He does not need to further apply some interpretation on what you have said and all that. All that is not. Okay. So how does this resolve the receiver's dilemma? One second. How does this resolve the receiver's dilemma? The receiver picks a subset and includes only those in the questionnaire. If the sender's sequence is amongst the responses, so the sender's history is actually amongst the responses that are available there, he takes that. If it is not, he just picks whatever is the best that applies, the one that maximizes his utility amongst the options available. Now, this might seem like this is not fair and all that, but you actually go to to the US airports and all that, you will find that this kind of ill-posed questionnaires or something, quote unquote ill-posed questions are often present. you have to, especially in taxation and so on, you will find that only a few options are there. You have to pick only the one that applies. इसमें से कुछ बोलो. Okay. Don't tell me, oh, no, my story was this. No, I want to know one of these. Okay. So, thus all senders with histories in the responses that are included are correctly identified. Because it's an independent set, the sender does not have an incentive to misreport one option as the other. So, if his history is the true history, it will get correctly identified. Okay. So, and in fact, this is again aside, if there's this field of game theory called mechanism design, from there is this concept of incentive compatibility. So if it turns out that the utility is incentive compatible, you can recover everything. Okay, so this basically relates, sort of information theory to incentive compatibility. So what the receiver is basically doing is ensuring the desired outcome by constraining what can be said. Okay, yeah.
It is like introduce a partial order between X in possible responses in this way. That uses a directed graph.
No, it's if either. This is symmetric, yeah. If either of these hold.
But then, by choosing an independent set, then aren't you ignoring, say...
No, that's why this is a theorem. This is actually correct. This is what you need to do. So we initially thought that one should look at a directed graph. So it turns out, so essentially to give you intuition, what happens is the receiver, because it's a receiver commitment first setting, right? The receiver does not know whether it's X who's going to come or Y who's going to come. So he has to be prepared for both. And that's why you need the undirected graph. Anytime you look at one situation, the symmetric other one is also possible. And that's the reason for it. And this is a zero error setting, so that's why there's a lot of symmetry involved as well. Yeah. You and Aniket, you had okay. All right. So basically, as I said, what I'm doing here is I'm constraining what can be discussed, what is on the agenda, what people can actually say uh, as a response to my questionnaire, and then using that as an instrument to get information. Okay, that's basically that's basically the the trick here. Okay. Now you can ask, okay, how? So if the largest independent set is what you can recover, what is the rate? Okay, so now you can go through, rattle through an information theoretic analysis of this. So you can define this, the nth root as limit of this, take limit as n tends to infinity, define this as the information extraction capacity of a sender. This is the maximum information asymptotically that you can get from a sender, and it's a function of the utility u. So if this capacity is greater than 1, it means that there is some non-trivial amount of information you can get. Okay, so is this greater than 1 or is it equal to 1? So it turns out that you have actually this bound. So you can take the graph for n equal to 1. The largest independent set of that actually lower bounds the capacity. Yeah. So that is an achievable strategy. One achievable strategy. There could be other ones. This is one achievable strategy. No, the capacity. So in every Stackelberg equilibrium, you recover this much. So I'm just defining the capacity through this quantity. This is a good point. Actually, you will see later a different model in which the capacity the amount of information you recovered is a function of the equilibrium itself. So in this case, it's not like that, but you will see another model like that. But anyway, so what does this mean? This capacity is greater than equal to the independence number of the base graph, that means the graph for n equal to 1, which means unless GS is complete, right? A complete graph means one which has everything is connected to everything. So if GS is not complete, then this is greater than 1, which means unless this guy is a pathological liar, there is some non-trivial amount of information you can get from it by doing this. Okay. In fact, I can even show that later if I have the time. There are examples where even in a complete graph you can get non-trivial information. So this is an inequality here, remember. So you can get a better bound, and even in a complete graph you can get non-trivial information. So essentially, what this is doing is we are building this thing, right? Where you stare at a utility function and tell me, okay, how much information content is there in this utility? Just like you look at a probability distribution and ask, okay, how much information content is there? So in a certain operational setting in which the receiver commits first and the sender responds, and there is this questionnaire design setting, we are asking, okay, how much information can be recovered? Right? Okay. It has all these super multiplicativity properties and all that sort of stuff. I'll just run over this. One interesting thing is this generalizes Shannon capacity actually. Generalizes the Shannon capacity of the graph. So it's super hard to compute as a result of that. Uh, uh, and but you can get computable bounds, through some optimization, lower bounds and all that. You can create some lower, you can get some bound, and the lower bound actually comes. I'll just tell you the interesting thing about that lower bound is that essentially what it says is that if you can find a subset of X of the locations in which every chain of lies like this is non-profitable, then that size of that subset is a lower bound to the capacity. So a chain of lies is like this. So you report I1 to I2, I2 to I3, I3 to I4, etc., IK to I1. Create this kind of a circle of lies. If this circle chain of lies is non-profitable, that means that sum of the utilities from this is less than zero, then that subset, the size of that subset is a lower bound on your capacity. So the larger, in fact, the asymptotically, actually, you can show that that is actually what the largest size of such a cycle in in a certain asymptotic sense is actually equal to the capacity. Okay, and because there was a symmetry involved, as I said, the symmetric part of the utility actually plays a role. So you can think of a utility as a matrix, right? So every matrix can be written as symmetric plus skew symmetric matrix. So this is basically the symmetric part of that. So it's uij plus uji plus divided by 2. Now this is another utility. This will have its own center graph. It will have its own capacity. Okay, and you can use this actually to bound. So I'll show you where this shows up. It shows up here. So the capacity of a sender is less than equal to the Shannon capacity of the graph of the symmetric utility. Okay, so essentially what this is doing is basically coming up with, so this is your converse, essentially the converse. Now why is this important? So this is important because what this is showing is that this is in general going to be the Shannon capacity of a graph is less than is less than the number of vertices, right? So is in general strictly less than Q. So what this is showing is that this guy here is in general strictly less than Q, which means so operationally what does this mean? This means that your optimal questionnaire should not be scaling as Q raised to n. Even though your number of locations is Q raised to n, the optimal questionnaire, the how big a paper do you want to print your questionnaire, should not be growing at Q raised to n. It has to scale at something strictly less than Q raised to n. Okay. Now this is interesting. That means even if you had a very big sheet of paper, you don't want to use all of it. So this is very different from the cooperative communication setting. In a cooperative communication, if you have a big sheet of paper or if you had basically a noiseless channel with lots of inputs, you want to use all of that, and that gives you better communication. Here, beyond a point, that doesn't matter. The optimal channel resources you need is actually is even in the Shannon setting, more channel resources lead to better communication. Here, more channel resources beyond a point don't matter. So there's an optimal number of channel resources that you need. Okay, so 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 essentially, what you can say is that in the cooperative setting where the sender and receiver are cooperating to communicate, right? What you care about is capacity of the medium. Here, the question is not capacity, but capacity utilization. How much of that capacity should you really be utilizing? In fact, if you overutilize, you will again go down. You will create too much room to lie, and you will start recovering less information. Yeah, it is. As I said, no, this capacity is always greater than one. Yeah, except in a trivial case, it's greater than one. And thanks to this, you also have there's this bound through Loas theta. This is a lowest theta function of on bound on Shannon capacity. So this here, so I don't know those of you who know this here. This part is called Lowash's sandwich theorem. This is Shannon capacity, this is lowest theta, and this is alpha. So here you have now the information extraction capacity of the sender sitting between these two. So this is now because there's one more layer of cheese or bread or whatever. It's a club sandwich there. Nobody's laughing. Okay, and you can then, of course, in the case, you can once there is some chain of inequalities like this, you can ask when is the equality true throughout and all that, and they will get some results. Okay, so when G is a perfect graph, there is equality. So now quickly I'll rattle through the noisy version. Now noisy version, here's the, so you have a channel again, some DMC here. Again, you want a zero error setting. Okay, so it turns out that the amount of information you can extract is this minimum of these two, the extraction capacity of the sender and the zero error capacity of the channel. So what this means is, if you have, this is again sort of again the same theme that I just mentioned, that if you had even if you have a very high capacity channel, you are still limited by what, by the dishonesty of the sender. Okay, that is what's limiting you. The minimum of these two is what dominate. Of course, if the channel capacity itself is low, then you will not be able to get much, and that is it's also reflected. So essentially, I mean, I think of this as sort of the non-cooperative analog version of the entropy of a source. Essentially, like whatever the role that the entropy of a source plays in quantifying how much information content is present in it is essentially the utility, the capacity of the utility is playing some role like that. Okay, yeah. So as I said, it plays the role analogous to that of the entropy of a source, and U is analogous to its PMF. Even with unit rate noiseless communication, the receiver may not want to utilize all the available capacity. More channel capacity does not imply a better communication. The optimal channel resources required is actually the extraction capacity of the sender. So I will tell you. So this ends this one case study on with receiver commitment. I'll take questions if there are there, and then we'll move to sender commitment. No questions? Any questions from the audience? Okay, you have half an hour to go.
Is there any practical channel that follows this?
I don't think the physical channel will not have this thing. This is the property of the strategic setting. It's a function of it's the utility that's creating this. Maybe, but com engineers can maybe say more. I'm not sure about it. Yeah. Okay. Okay, you can do a stochastic model, but I think I'll skip through this. This is so stochastic model again. We have the same sort of thing. The main thing is you have a Shannon rate region, which is an entropy in the information theoretic setting. The rate region is entropy of the. So stochastic setting means that the type is basically your x is chosen IID according to some probability distribution, and you have some the receiver now wants to minimize the probability of excess distortion. Okay, so some rate distortion type of setting. The information theoretic setting, the channel resources that you need are these, right? So it says that anything above any compression above rate h of p is okay. Now, in the strategic setting, this having more resource can be redundant. So it turns out that there is actually, so I've skipped those slides, but the rate region in the strategic setting is a convex set, and it's a strict subset of h of p to 1. That's the interesting thing we find. Okay, so now let's go to sender commitment, which is the problem of influencing a receiver into taking an action. Again, we'll start with the zero error setting. Okay, and then we will zero error signaling, and then from there we will move to the Bayesian signaling. Yeah.
So there are multiple senders. Each of them can have a different degree of light that they can right? So how can we use the same strategy for all of them?
Yeah, so good question. Actually, so here, right? So it's a good question. Then maybe I'll just slow down here. See here, the sender's type is basically just the history. That's all we have here. If you see here, I will go back further. Back into sorry. What is the sender's? Sender is identified by his history, and the goal of the receiver is to identify as many correct histories as possible. Okay. Now you could have also an additional parameter here, which captures the degree of lying, for example. Here, the function, the preference for lying or not lying is a function of just the history. That's all. Then all senders have the same uniform preference. We could have an additional parameter in which that there is some degree type of thing present there. And that will also be a thing that is a source of incomplete information. Basically, a receiver will not know whether he has a whether this guy has whether he's an honest sender or not an honest sender, and so on. So that could be and that results in a different concept. It turns out that you can take something like a weighted independent set, weighted sum of independent sets, actually something like that is we've done that, but it's mathematically extremely messy, and to calculate, to do all these asymptotic analysis in that is very hard. So so that's why I skipped through any of that. But yes, this is possible, and it's a very reasonable question. We've tried to investigate it, but yeah, it's not a very clean answer there. Right.
But can you give some bound?
Yeah. So we've tried to give bounds. Yeah. But they are not. They're very messy, as I said. It's not as. Yeah, there's nothing illuminating to include in a tutorial in that. It's just more or less a mechanical but tedious extension of this, of what I already have.
Just to additional comment.
Yeah.
Like from coding theory point of view, we can define a typical set. Right? And for each sender, the set may be smaller or bigger depending on the amount of noise that he's adding.
Right.
And among that, worst case user you can pick and then give that or
so you can so okay, yes, good question. So here the model that I was referring to is one. Let me just write it here. So if you have an additional parameter, right? You have an additional parameter. So here our utility is a function of x hat comma x, and I put in suppose an additional parameter lambda, which is the degree of truth telling, degree of honesty. Now, if I want to maximize the this, this is the hard. This one is hard. Okay. So this here is the weighted size of the largest maximum number of correct histories that I can recover. Okay, or average number of correct histories that I can recover across all this. That is hard. The easier one is this. So if I do min over lambda, okay, so the worst case over that this thing, that is easier, because then you have to just identify which sender type, as you said, you're looking for, and then you can do. I mean, in this case, typicality doesn't play that much of a role, but yeah, you can. Yeah, it's essential. So in the stochastic setting, yes, it does play a role, but in the zero error setting, it has no role. But yeah, you can look at the worst case and try to info that. But remember, we are in this.
Also, the lambda plays the role of the noise.
Lambda plays the role of, so there is lambda also plays the role of the noise. Lambda and utility both play the role of the noise. Essentially, a source. I mean, we can't call it noise in the standard sense. It's this thing of uh, some misreporting.
Here, then you don't have information about.
Yes. So it is some source of misreporting. Let's put it that way. I mean, it's not. I cannot put this thing. I mean, I cannot model it as noise in the standard. Yeah. Any other questions? Quickly run through the last one. So zero error signaling. So here now what is happening is physically the setting is that now there's no questionnaire or anything already printed. The sender just comes and starts talking. And his aim is to influence the receiver into taking an action which is most beneficial to him. Okay, so the sender wants to maximize his utility. Receiver wants to maximize the number of signals recovered. Okay, and I'm not putting n here because that's not that important. Uh, so what's happening is therefore the sender is trying to influence and knowing that the receiver is trying to decode. Okay, knowing that the receiver is trying to recover the truth. And in the course of this interaction, how much can the receiver recover? So this is information revelation, okay, where information is being revealed as part of this thing. It's not intended, it is not communicated in the sense that it's not being, in the sense that it is not actually being sent to you explicitly, but it is being revealed as part of this process of influence. Okay, so the question is how much information can be revealed with this fellow who's trying to influence you. What can you learn about it? Okay. Again, you can write out a Stackelberg equilibrium now with sender commitment first, and you have okay. Now here are the so here's one simple observation. Here, zero error setting, right? So simple observation. So suppose y is what the receiver sees. What can the now if the receiver sees y, what can and the sender has already declared it's a sender commitment problem. So sender has already declared his S, his strategy S. What will the receiver do? What can the receiver recover? The receiver can recover the pre-image of y, right? He knows S, right? He knows S, so he'll recover the pre-image of he'll know the pre-image of y, of y. So in fact, the receiver can recover one and exactly one element from every element y in the range of S. Sorry, one and only one element from S inverse of y for every y in the range of S. So therefore, the number of x's that are correctly recovered is actually equal to range of S. Size of the range of S. That's it. It's very simple. Okay. Now call this the worst case utility of the sender. Okay. So now out of the things that the receiver wants to recover, things that the receiver ends up recovering, the receiver is going to map the y that he gets to one of his pre-images, one of the pre-images of it of y. But which of them is most beneficial to the sender, is a question mark. So the sender looks at the worst case out of that. That's what is called the worst case utility. And then UXX is the utility of correct recovery. So in the case when the receiver correctly decode, then the utility that the sender gets is UXX. Of course, the sender may want the receiver to incorrectly recover. That's a different matter. But these are two functions. Okay. Now it turns out that here's you in stack. If S star is a Stackelberg strategy, equilibrium strategy of the sender, then you always have this. But the worst case utility is actually equal to the utility of the correct recovery. So in the worst case, what is happening in this game is that the utility that the receiver gets is actually equal to the utility of correct that he would get in correct recovery. Okay, so therefore what this means is, so now consider so what this means is the following. So consider a sender with a utility u. S star is a Stackelberg equilibrium strategy of the sender if and only if the following holds. Okay, so you create the P of S star here. Sorry, this is my abuse of notation here. This is basically all the partitions created by S star. So actually ignore this. Let's read this. So what the sender does is he creates this graph G bar S in which there is an edge if between I and j if UII is less than UIJ and UJJ is less than UJI. So earlier remember there was a or, now there is an and between the same. Okay, so he looks at this graph in which two x's are I and j have an edge if he has an incentive to report I as j and j as I. And what he does is for every click in that graph, he sends a unique signal to the sender, to the receiver. The receiver now looks at this signal that has come and he can map it back to one element in that click. Okay, so he can recover what the sender wanted to say at the level of the granularity of these cliques. That is all he can recover. So which means what? The number of symbols recovered by the receiver when the sender plays a Stackelberg strategy S star is actually equal to the number of cliques that are created in that particular strategy that he's considering. So he basically can divide the graph into cliques in multiple ways. Every one of each partitioning into cliques results in one Stackelberg equilibrium strategy. Okay, so it's now the number varies with the Stackelberg equilibrium under consideration. This is what you had asked, right? So the amount of information you extract, the receiver can recover depends on which Stackelberg equilibrium strategy the sender has chosen. Okay, so you can then ask, okay, what is the minimum you can get through this sort of interaction? What is the minimum amount of information the receiver can glean through this interaction? Considering that sender can play any Stackelberg strategy, right? And it turns out, well, that is nothing but the clique cover number of this graph. The minimum amount of information you can get. You create this, basically you have this utility, from that utility you create the graph, find the clique cover number of that graph. That means the minimum number of cliques by which you can cover that graph, and that is actually equal to the amount of information. So we call this a quantity, we have given it a name, we call it the informativeness of a sender. How informative is an interaction with the sender? The informativeness of a utility. Properties that it has some interesting properties. So it's always greater than the extraction capacity for the same utility. This is always it turns out there is always this. In fact, when U is symmetric, they are actually mathematical programming duals of each other. One is a primal problem, the other is a dual problem. So you have switched the order of play, and the information quantity that comes out of this to a very natural way actually switches from primal to dual. That's something that it's a fascinating thing. We don't still know what the what the full implications of this are. But the important thing is, in general, because these are both discrete optimizations, right? And there's going to be a integrality gap here, or a duality gap here. It means that the order of play matters. Who commits first matters. So this is some, sender commitment, the information content in the utility is different, and receiver commitment, the information content is different. So you get two different notions, two different quantities, and this is a unique aspect of a non-cooperative setting. The cooperative setting there is no reference to anything like this in a cooperative setting. Okay, 15 minutes. Okay. All right. So, any questions on this? So I'll just go over this once again. Essentially, what's happening is that the sender, you create this. In this one, you have this. You can create this sort of graph that I just mentioned, and now you can divide this graph into cliques in multiple ways. For example, you can take one clique. One possible clique is that you take this vertex, this vertex, this vertex, and you take this vertex and this vertex. These are both cliques. This is a way to cover the graph with cliques. Now, for each of these cliques, the sender will send one signal. So he sends a signal, say sigma 1 here, and a signal sigma 2 here. Now, and from there, then the receiver recovers that when he gets sigma 1, he says that, okay, yeah, one of these dots was sent. Okay, and when he gets sigma 2, he recovers that one of the x's was sent. Okay, but the sender can also do other things, like for the same graph. The sender can also say, well, let me break it up into cliques in the following way. I create, here is suppose one x here. This is one clique. This is another clique. And this singleton vertex is another clique. So now he can send us a signal, another separate one signal for this, one signal for this, and one signal for this. Now the receiver can recover three things. He can when he gets sigma 1, he knows that x was sent, one of the x's was sent. When he sends sigma 2, he knows that one of the dots was sent, and when he sends sigma 3, he knows the star was sent. Okay, so the amount, all of these are equilibrium strategies for the sender. they all give him the same utility, but they give different amounts of information to the receiver. Because you remember, in a Stackelberg equilibrium, the sender commitment means sender's utility is being optimized and receiver is responding. So receiver can get different amounts of information from this strategy, right? Now, so all of these give the same utility to the sender, but they are not identical for the receiver. So you can then ask, okay, how much, what? So, so physically, what we think of in game theory is that any of these could have been possible outcomes of this interaction. So through this interaction, what is the minimum you can get is becomes the question, and the minimum is the minimum number of cliques you need to cover such a graph. That's your clique cover. That's the information motion. Is clear? You can do asymptotics on this also. They're interesting. Actually, I told you the club sandwich theorem, right? The club sandwich theorem now extends also on this side. Remember that was on this side. It actually, you get a very big sandwich, many layers on this side and layers on this side as well. Hmm. Yeah, good question. I don't have an answer to that. But tossing a coin in a different angle, in a different aspect, yes, there is a okay. So here this is zero error, and the sender and receiver are playing deterministic strategies. Okay. Now in the receiver commitment, there is no scope for randomization. Rather there is scope for randomization, but there is no benefit to randomization. It turns out. But in the sender commitment, there could be benefit to randomization. But because we are looking at a zero error cost function, right? There are some weird discontinuities that come up. It's basically not linear in the probability distribution anymore. A zero error cost function. So there are discontinuities that show up, and then therefore then the existence of Stackelberg equilibrium is under question. And so we've shown counter examples and all that. So I don't want to get into that. It's a slightly technical, more mathematical topic than anything else. You get some weird discontinuities where sender is want to recovering more, so receiver is attempting to recover more, but then in the process gets nothing. Some jump kind of thing happens. So anyway, the stochastic signaling is a very important thing. Okay? There is some role to that, because at the end of the day, signaling is about shaping the posterior distribution. And the stochasticity is a question. I mean, I don't have an answer to it fully in this model. So there is an answer to it in this model. So let me just quickly tell you. I don't have. I'll just briefly. This paper is a very nice paper, and you should go through the proofs and all that offline later. So, but I'll just tell you just an overview of this so that you know how to mentally think about this. So sender and receiver are engaged in a. So here this is a large block length setting. So what they are engaged in is basically, you can think of as a series of identical persuasion problems. Okay, sender is trying to persuade the receiver, but so the example they give in the paper is actually very nice. So sender has a bunch of projects that he wants to get funded. Receiver is the fellow who's going to fund. Now, suppose the sender has there is a limitation on the communication capacity. Okay, so basically so sender would ideally like 1 unit of time per project, but he's been although he has n projects, he has been given only n/2 units of time. Now, a naive thing to do is to say, okay, well, I'm going to focus on only half the projects, and I'm going to sell only half the projects to the receiver. But instead, what you can do is coding. What you can do is come up with a strategy that works on tuples of projects or triples of projects or whatever. Okay, let's say tuples of projects. You bunch projects together and send a signal for each bunch. Okay, so you take. So if you had, say, if you had, let's say, five projects, you take, you create pairs of projects. That will be 5 times 5, 25 such pairs, and for each pair you send a signal. Effectively, I mean, for this audience, it should be clear. This is basically, you are sending a code. You're doing coding here. For every block, you are sending a signal to the receiver. Okay. Now it turns out this actually helps. This is better than just a priori selecting projects and then focusing on just those. a priori selecting would have been basically doing doing no coding, essentially just or you are just effectively just removing some part of the message space direct at the very outset. So the model is like this. Both sender and receiver here have a utility function. It's a persuasion setting. So the receiver takes an action. Sender receiver setting. Receiver takes an action. Sender has the information, and there is a communication channel in between which has some capacity. Okay. So this is the sequence of projects or sender types. This is the sequence of actions chosen by the receiver. What the receiver is going to, okay, he's going to say recommended, not recommended, recommended, not recommended for those projects. Okay, and the channel can be used k times. So xk is your channel input, vector of channel input. This is a vector of channel output. There's some noise in the channel. That's your channel law. So the sender strategy payoffs are given in this way, and sender strategy is therefore now a distribution on this. It's a distribution from the signal space or this project space to the inputs to the channel. Okay, you can again sender commitment. So you can write out a Stackelberg payoff for the sender. So sequence of plays, sender announces a strategy. Nature picks a sequence of projects. Wn is omega n is drawn IID according to some prior mu, and then he maps omega n to xk, which is your channel input. Xk comes out as yk, and then based on yk, receiver chooses which projects to fund. Okay, so this is the best response of the receiver, senders, and senders Stackelberg payoff. Okay. Now this is so just note the notation here. This is capital US star, which is the best response of which is the senders Stackelberg payoff. Now, how do you? So the thing that they find is the sender Stackelberg payoff can be characterized through this particular optimization problem, which is a single letter optimization. There's no block length reference here. A single letter optimization. And what is there here? There is this small US star. Small US star is the worst case payoff that the sender would receive. Okay, when the receiver has a posterior belief new about your omega. Okay, so when his posterior belief is new, the receiver will pick an action to maximize his utility. The worst case, you look at the worst case action under that this thing. Look at the expected payoff for the sender. This is the small US star as a function of that posterior belief. Okay. Now this posterior belief itself is going to be a function of the signal you send and all that. So, but this is you can write this for every such belief, and you write out this what is called the splitting problem. So, what is the splitting problem? This is optimizing this weighted sum of these posterior belief payoffs, lambda m, US star, nu m. Okay, subject to the condition. And what are the variables here? Lambda m and vm. These are supposed to be these are the lambda m and vm are so lambda. So m here stands for a message. Okay, I'll tell you what the message is. And nu m is the posterior belief that the receiver will have in case of when the message is m. Okay, a message is not what the receiver hears. Okay, receiver hears something else, which is noisy and all that. Oh, forget that for the moment. But the m is for the moment going to stand for a message, and it's just an index for us. So this summation is over all lambda m nu m, such that they are the omega marginal that you get from this is equal to mu. So if I marginalize this over m, I'll get a marginal distribution of omega, and that is equal to mu. And there is the capacity constraint. What I have here on the left is the mutual information between omega and m, and that has to be less than equal to some c. Let's say I'm putting c as some constant. So the value of this optimization. So this is basically calculating the worst case utility that the sender can receive when he has a splitting of the when he has a splitting or a when he has a joint distribution on the prior and message space given by lambda m nu m. Okay, and the new M is the posterior that that the receiver is going to recover. Okay, so this is just an optimization problem, and what they basically show is that the main theorem is this. So if you take the large block length limit and take the Stackelberg payoff of the sender, it turns that, and you let this kj by nj, the rate here or inverse of the rate here, go to r, and that is then this limit here is equal to v times v of mu times mu comma r times c of q. Okay, the value of this single letter optimization. Okay, so the proof sketch is basically this. So you remember, so so I'll tell you what the basic thinking is. See, you use what you want to do is the following. I'll actually skip further. I'll try to. This is probably a better way to explain it. See, the optimal splitting problem that I just wrote, it defines a set of beliefs that give the beliefs that the receiver ought to have to give the maximum worst case payoff for the sender. Okay, what are the beliefs that the receiver should have in order for the to give the maximum worst case payoff for the sender? So it just defines single letter beliefs. Okay, now the index that defines that set of beliefs actually becomes messages that the receiver wants to send. And what you want is that when you send such messages, the receiver should compute a posterior distribution from the sequence that is getting in the channel, such that that posterior distribution matches with the target beliefs that you have from that optimization. Okay, the receiver, in the process of picking an action that maximizes his utility, okay, should have had a set of beliefs which should become close to the posterior beliefs that you get when you send him a sequence of messages over this channel. Essentially, that's the main result that they end up with. Okay, so so you basically consider any yeah, so every signal that the sender sends must, by data processing inequality, satisfy this, so that you get an achievability type result. But this hard part is basically that you consider any splitting, and what you want to show is to show the converse type result. What you want to show is consider any splitting, and what you then for every any splitting lambda and mu m, want to show that for every epsilon greater than 0, there is a signaling strategy for the sender such that the payoff of the sender is greater than equal to this. That's how you get to that supremum there. So first is you do some interiority argument, and then from basically you do this. You basically, from joint source channel coding, you create this intermediate F1 which maps your project space to a message space. Okay, your omega n maps to mn, mn is mapped to xn, yn is mapped back to it, back to mn. So essentially, then effectively effectively what you need to do is make sure that you create the right sort of intermediate message space. So this message here is basically just a mental construct. It is only a construct that you have for numbering the posteriors that maximize the the splitting that maximizes your pair. Okay. Now, so the receiver is not guaranteed to do a decoding, but he does do Bayes rule. Okay. So what you want therefore is from the block the block of channel outputs that the receiver has got, he applies Bayes rule, and that should end up matching with that new one. Effectively, that's all that is what you eventually have to show. And so it turns out that you need to basically bound a bunch of things that look like typical sets. Basically, if you see here, there's some frequency, there's some some T alpha here, which is these are the number of times at which the posterior does not match with the correct with the intended posterior, etc., etc. You do that, and then you try to control. You basically show that this can be controlled. And essentially, that's the idea. Is essentially so the construction in the main lemma is essentially ensuring that the posterior that the receiver computes mostly recovers the right message or beliefs intended by the sender. Okay, that's basically it. Okay, so references for since students asked for general game theory. I know it's been a long this thing. General game theory, you can There are these two I would recommend. First one is particularly nice. For signaling and any kind signaling, screening, and any kind of communication in games, look at Myerison's book. The strategic communication, the zero error versions, there were two of them which with in the screening setting you have these are my papers here. The strategic setting, the signaling setting one, this one is mine. The others are this I'll let use. There are generalizations also, by the way, multiple receivers and so on. There are plenty of generalizations you can look at. I just recently saw a paper on Gray Weiner and all that. So plenty of various types of generalizations are possible. Okay, so with that I'll end. Thank you. We'll take more questions if there are any questions. Okay. Any questions from?
So how difficult is this to generalize to multiple agents?
See, sender receiver, multiple agents, even the cooperative setting is not that easy. Okay, you start getting into things like broadcast channel, and solve problems. But that I mean there could I am there are there are some sort of technical difficulties. Okay, technical difficulties are of the kind that all this best response, wagera. This results in a particular type of mathematics which requires you need to establish some continuity, this that which people take for granted in the usual setting. So there are so that is there. Uh, we're just kind of exploring this thing here. It's just the surface, but I think that is there. The other is I think my feeling is that right now the correct notions and all that are still being set up. So that also is a bit of a it's part. I mean, but I think that also is an opportunity. Let's say. So multiple, say for example, multiple senders or multiple receivers. What should be the correct notion of information? That becomes it's a question that has to be somewhat deliberated on. It's not that straightforward. Any other? Okay.
Let's thank the speaker and
Yeah, thank you. Thank you.
Okay.